Hello, this is a hands-on machine learning with multilingual image text fashion dataset. So in this session, you will be able to experiment with zero-shot clip classification and image search with the largest multilingual image text classification dataset and benchmark called GLAMI 1M. So in this session, we will be using a Python notebook executed within the Google's Colab, where we will real-time execute code, and we will do a couple of experiments that you can reproduce on your own. So you can go on now, click File, and save a copy of this notebook, and you can execute it, make changes, and the same as I will be doing now. So we will be working with this dataset called GLAMI 1M that we released recently. The dataset is composed of items where for each one we have an image and textual description, source country, and the category name. Each of the category names were assigned in the at least within the testing set part of the dataset were assigned by humans, and majority is assigned by humans. And we have within the dataset we have around 1.1 million items and 191 fashion categories. And we will experiment with this using a popular model called CLIP, where we will, regardless of the different languages that are available, we have 13 languages, we will be able to do classification and search. Hello, I'm Václav Košař. I'm machine learning engineer at GLAMI. GLAMI is a fashion search engine which utilizes various machine learning techniques to connect customers to e-shops. And okay, this is a part of a series of meetups which you can join. You can find us at the Midon meetup page. A link will be provided at the end of the session. If you have any questions, you can ask below the published video or any other social platform, and I will try to answer it. Okay, more about the GLAMI 1M dataset. So GLAMI 1M contains 1.1 million fashion items, 900,000 unique images, 1 million unique texts, 13 languages, mostly European, 191 fine-grained categories, and we have many categories, and some of them I don't even know. So, for example, we have 15 shoe types. Are you familiar with many different types of shoes? So maybe this is something you can as well learn. It's sometimes surprising. So we also have high quality annotation from professional curators which actually understand all of these categories, and this dataset actually as well poses a difficult production classification industry problem, and you can try your best in this dataset. You can outperform our models. The benchmark is available on Papers with Code. So here we can see the items we will have. We will see more of them within the notebook. So as mentioned, for example, we have an image, country code, name and description in a corresponding language. We have a target category and source of the label, which can distinguish between the human labels and rule-based labels, where most of the data set is humanly labeled and 100% of the test set is humanly labeled. In GLAMI 1M, a small amount of categories form a large portion of the dataset, meaning that the distribution of the product items across the product categories is highly long-tailed, which is a common occurrence, common problem in industry data, which you need to deal with depending on what you need from this. Do you need excellent performance, on those low occurrence categories or not. It depends on your problem. Also, we have a varying distribution between the different languages. You can have a look at this here. So you have Slovakian, Lithuanian, Czech, Turkey, Bulgarian, Hungarian, Croatian, Greek, Romanian, Estonian, Slovenian, Spanish, Latvian. And for example, Greece uses Greek text, and in Bulgaria we have a Cyrillic text, and all of these texts needs to be handled by the models, and we will see an example of how you can do this. And so GLAMI-1M is the largest multilingual image text classification dataset. So in this category, it is the biggest, and it is because we have the multiple languages. If we step back and say, okay, we disregard the number of languages, then we would be the second largest image text classification dataset. Second to recipe 1M, but contrary to recipe 1M, we have more human labels. In fashion domain, GLAMI-1M is the biggest classification dataset because we have the most categories and most samples. And GLAMI-1M is indeed smaller than open source web scrape dataset like Lion 5B, but that dataset is not suitable for classification tasks. There are no labels there. However, in this notebook, we will be using very interesting model called Multilingual Clip, which was trained on Lion 5B, and we will see what we can do with that. So the paper authors of GLAMI-1M are me, Václav Košař, and Antonín Skovec, Milan Schulz, Radek Bartizal, and funding institutions are GLAMI, Rosum, Czech Technical University Faculty of Science and Nuclear Engineering. This paper was published at British Machine Vision Conference 2022, BMVC in short. There are various links you can use over here. Okay, let's talk about encoding images, texts, and categories into similar numbers. So what we will be doing in this notebook is that we will be converting images, converting texture descriptions corresponding to those images into numbers that will be in some sense close together. And if we can do this well, we can actually use this as well. We can use the information from image, we can use the information from text, and we can do this we can join this information and then together perform classification. We can as well perform search. We can perform search from text to image. We can perform as well search image to image. So what we effectively will be talking here about is that we will turn image bits within the computer into a special array of numbers called vector embedding. Meaning that we will translate the bits of the image in such numbers that two images that are similar for a person, for a human, will be encoded in the similar numbers, and this is something which is super interesting. So we will be basically again turning an image into a series of numbers which represent the point in a space. You know, you could say, okay, two-dimensional space is a point on a paper, three-dimensional space is a point in a room, and here we will be translating into 512 dimensional space. And we will be working with image and with text, which means that's something that's called multimodal, and we will be also dealing with multiple languages. So that's called multilingual. And because we will be doing this encoding in a very smart way using this smart model, we will be encoding both image and text into similar place. And doing this, we can have this cross-modal capabilities. Now, how we can actually do this? So thanks to the powerful computers and data from the internet, we can learn special mapping functions from the bits of text and bit representations of images within computers, and we can map them into such points in space that in such a way that we preserve semantic similarities as perceived by humans. And so similar images for human will be close points together in this 500-dimensional space. Finding this mapping is called training. It's a learning of a model within a computer where we have lots of numbers that are doing some multiplications and summations on the bits of the image. They do this step by step in a compounding way, such that at the end a sequence of numbers pops out which represent this point in the multi-dimensional space. And because we can encode text, we can as well later use this to encode a category. If you can describe a category of a product in a text, then we have a text which we can encode into this space. And if we can encode all information about the product in this same place, then we can then use the information for the product to find out which category the product corresponds to. And the more information we have about the product, the more this information will complement each other, and we can achieve higher quality classification. And one of the additional interesting things is this ability to deal with multiple languages. This is important, especially in systems where you would like to have some asymmetry, which can save you resources, where you don't have to deal with every country, every language individually. You can actually train model across all of them, which can then the larger resource countries will then, in some cases, improve performance of the model on the smaller resource countries, actually. Okay, so you can make a copy of this notebook, because now we are going to the section where we will be executing the notebook. So you can make a copy using this file and save copy in a drive, and then you can execute it. Okay, so I will be executing this notebook. Let me check the runtime. I would actually like to have graphical computing unit acceleration. So now the notebook is initializing for me. And I will be using a graphical unit, but if you cannot get a GPU, maybe you can get a computing processing unit instead, which will be a little bit slower, but I haven't tested it, but it should work as well. So what we do at the beginning is that I'm going to check out the GLAMI 1M code repository and enter it, such that we can use the code stored in there. After that, I will install all dependency libraries from public repositories. Here we are installing also open source libraries for downloading on open source models. One of the models was trained by OpenAI. Some other models were trained by open source organizations. Okay, so this is downloading. After that, since we updated the environment, we will need to restart the machine, which is fine. And okay, where are we? So okay, we are installing various dependencies for dealing with calculations on large amounts of data, either on our CPU or on GPU. Also libraries dealing with tabular data, so operation on tables, libraries to display images of charts, libraries to calculate statistical properties of the results, and various other acceleration libraries for calculating on GPU. Okay, will be just a minute, and after that we will be as well downloading part of the dataset. Okay, so now we need to restart the runtime as mentioned, and we will need to execute this part, but no longer installing the requirements because they are installed. Okay, so now we will download part of the dataset. Because the dataset is quite large, it will take 30 minutes, but instead I'm gonna download only a smaller version of the dataset, only the part that is used for testing. Usually in machine learning we split the dataset into training set and testing set. The training set is used during training of the model. Is usually 90% of the dataset, and then the testing set is usually 10% of the dataset. And we do this such that we can test the generalization properties of our models. So the test set is actually never seen by the model, so we would like to see how well it generalizes into on data the model haven't seen before. Okay, the data set, which is actually 10%, around 100,000 of items, is 1.1 or 1.4 gigabytes, and we will be downloaded within a minute. After that, we will load the dataset into a table which we can then use to interactively display the items that we have. Okay, now we are unzipping. The dataset itself is stored on a Hugging Face repository, which allows you quick download and quick access, and as well communication and versioning of the data. So you can find our dataset there. Okay, so dataset was downloaded. I called a function to actually load the test set into computer memory, and I sampled 10 items from it. I printed those items over here. We can see that we have a item ID, image ID, name, description, category name, and image file for each of the items. We can see that we have multiple languages and multiple text types. We can see that we have various categories. And because this table is a little bit sad because we cannot see the images, let's actually display this. Let's use a function to display the items together. So we will convert the table into HTML and display the display section of the columns. So here we have a sneaker, we have a bomber jacket, trousers, I think these are moccasins, some forks, wallet, men's undergarment which looks like pants, shirt, which that's kids, girls t-shirts and shirts, and then we have a men's t-shirt, then we have a parka for men. Okay, so we have these kind of items. We have 10 items that we selected. Now let's play with these items. We will be to play with these items. We will actually load an open source model. One model is for encoding of the images, as I mentioned before, into 500 dimensional points in space. And this one was trained by OpenAI, and it was trained in such a way that they downloaded lots of images and corresponding captions from the internet, and they trained two-part model. So one part of the model encodes image, one part of the model encodes text, and they trained them in such a way that they map the text and image into same point or very close point in a space. We will also use another model which is available openly on the internet, which is called Multilingual clip. So this is a text encoder which can as well do this, which can as well encode text across many languages, across all languages we have actually available in the dataset. So it doesn't mind seeing Cyrillic or Greek text, it can encode them all. So these are the models that I'm downloading right now. Here, I loaded the OpenAI model, which turns the images into numbers, and now I am loading the multilingual text encoder, which converts text into points in space. Okay. These models are about 2 gigabytes in size. Similarly, they then take up the RAM or GPU video RAM. And to actually do calculations, you need to have sufficient computing unit, or use additional compression mechanisms, which here we are provided of the GPU from Google. Okay, it should be in a minute. Okay, so we almost downloaded the models. Now we will have a look at how large they are in terms of how many these numbers they have that they are then used for multiplication and summation. So we take this image data, should start as bits in the computer, then we do some multiplication, additions, and then we spit out these and another set of numbers which have some special properties. And so we will look here that the image model has 100. The image model has 100 million of parameters. The text model has 500 million of parameters. Okay, so that's a lot of numbers, but current computers can deal with them. Okay, now we take our 10 samples, we convert them to those 500-dimensional space, and then we will work with those vectors and discover their interesting properties. Okay, so what I'm doing in this cell is that I am going over all items, the 10 items that we sampled. I'm taking a text, I'm concatenating the name and description together, and I will use that as the input text. Then I'm opening the image and pre-processing it for the model. I'm transferring the image to the GPU. Also text is prepared and transferred to the GPU. I pass both image and text to the model. I perform the calculations from both of the image model and text model, and then I do some additional after processing for the comparison of the two vectors that we have. So now for each item I have two vectors which I can compare. I printed those vectors here as well in short format. So for each of the 10 items I have 500 numbers for image, 500 numbers of text. So those are some sort of numbers like this around 0. and we will play with them. Okay, so since we have those vectors, we can now compare them. We can, for each image, we can compare which each text, disregarding which item it corresponds. I can create a matrix of the similarities where the places which are the most similar, the texts which are the most similar to the images have the highest number here. This is not very visible, so let's display this in a graphical format. So we are displaying cosine similarity between text and image embeddings. And okay, let's see. So here we have a sneaker image. You can see like the most similar text for this sneaker is actually the corresponding textual description of the sneaker, which is actually written in Cyrillic text. For the bomber jacket, the most similar again is the description for that jacket, and the second most similar is this description for a parka jacket. Okay, so this seems to work very nicely. Yeah, okay, so we can see that the properties for the shirts as well are transferring. The problem here, for example, is this fork. While it works, we can see that it is similar. Okay, so there will be other issues with the forks later. Okay, so we have this display, and we can see the correspondence between the image and textual description. We can see that it doesn't matter what kind of language there was. And let's then, okay, so this was interesting, but we would like to categorize our items. And for each category, we have a textual name, so we can take the text and convert it in a special way into a format such that the encoding result is very close to what we have in the from the embeddings that we have. So I converted the categories in following format: a photo of men's sneakers, a type of a fashion product; a photo of a woman's bomber, a type of a fashion product; a photo of a man's pants, a type of a fashion product. Okay, so I converted 10 categories to the 10 items we have into this, and now we will have a look if we can actually find similarity between the categories and the items. I did a similar thing. I again compared, created a matrix. I will visualize that matrix. Okay, so now we have a cosine similarity between category prompt and image plus text embeddings. So I need as well representation for each of the items, since I have two things for each item: text and image representation. And they are very similar together. Here the best is actually to sum up and average the vectors together, and after that compare with the categories. If we compare with the categories, you can see that in general this approach does categorize correctly into these 10 categories. For example, sneakers are indeed going into the men's sneakers. The bomber jacket is going into the women's bombers, but also it's very close to men's parkas. And here we have the problem with the forks, as I mentioned before. We can see that the fork is saying that it should belong to the kitchen, but it's also thinking maybe it should be in men's pants or maybe in men's undergarments. So this methodology is not perfect, and we will as well see like these confusion. For example, men's undergarments seems to be belonging instead into men's pants. So this is not perfect approach, but if we can see it's doing something interesting. So we haven't trained for this at all. We just used language and image representation, and we are getting actually something out of the model. So this method, it's called zero shot. We haven't done any training. Okay, so this model was trained in unsupervised way without the labels. We are just using the testing set here, and it's already having some performance. So top 1 accuracy for this method is 32% on this data set. So that's kind of bad result, right? Like most of the time you're not going to classify correctly. If you look at the problem like in categorizing at least in top 5 most likely categories, are they correct? So then this model is 75% right. And you can look at the paper, you can look at the code, how you can execute the evaluation yourself, and you can as well compare to a training approach which achieves better performance. So instead of 32, the training approach is 75%. Okay, so now we would like to do the search experiment. So for that we need to create embeddings for the entire testing set, for the entire 100,000 items. That would take quite a bit of time. So I'm not going to execute it here because we would lose 13 minutes running things on the GPU. Instead, I will download pre-computed embeddings from Hugging Face quickly, and we will do the search on them. So what we will do in this search experiment is that we will use only the image vectors, the image numbers, and we will select one of the 10 items that I presented, and we will search entire 100,000 items in the testing set to find most similar items and sort them how similar they are. Okay, I'm downloading. After downloading the dataset of the embeddings, we will load those pre-computed outputs. We will unzip, load them into the computer memory, and after that we will have them when we will have them in the memory, it still will not be quite enough to make the search. To actually perform the search fast, you cannot, people don't have time waiting minutes for results. So you need to find some fast way how to do this. And if you are a programmer, you are familiar, you already have some ideas how you could do this. So in computer programming, there's this hashing principle, which is actually very easy to understand. So you can imagine that instead of comparing my item that I'm searching with each item, each 100,000 items, instead I will split the 100,000 items into similar buckets, and I will only first compare my item to the smaller number of buckets. I will find the buckets which are most likely to contain similar items, and then I will search only and compare only in those buckets my item that I actually have. So this is this hashing method. This hashing method, approximate nearest neighbor search, is quite accurate method, not 100%, because it depends. If you want real speed, you will be willing to do additional trade-offs, and maybe you will miss a couple of items, but it's a fine. And how you can actually construct these kind of buckets. You can do this because we are okay. So we have now 100 items. Each item is represented as a point in 500 dimensional space. Okay, for each item we have 500 numbers, and how we can find these sort of buckets. So actually, you can create these buckets in different ways, but the simplest way how you can do this is just take this cloud of points which represent the images, and you can just randomly split and you can randomly cut this cloud with some hyperplanes, and then just based on which side you are of the hyperplane, you can actually create these buckets. So it means that you will create these subsections of space because of those cuts, which will represent those buckets. The problems where you may lose some items is that when you exactly get very close to some of the hyperplanes, and then you will miss some very similar items which are however on the other side of the hyperplane. But in general, this is very accurate approach how you can very much speed up. You don't have to compare to all 100,000. You can just compare to a smaller smaller number of buckets, and then within those buckets, and you can of course cascade it. You can create a tree in this. So we will use for this method a library from Google called Scan, which can in milliseconds do the search for us here. So to do this, I will first build those buckets using this code, right? So I will take the array which contains the embeddings, which I just downloaded from the repository. I will take those vectors, split them into those buckets, and then store the buckets in a property called index. Now that takes a minute, but after that I will select from 10 of the samples. I will select one sample, which is a pants, and I will, for those pants, I will do the search on the index itself. Okay, we are still creating the index. Okay, we will have that in a minute. Okay, we created the index. I selected one of the items from the theme as we wanted. I took the image. I took its corresponding embedding over here, and I used that embedding to do search with the index, and I retrieved 4 neighbors and then displayed them over here. Now here we can see that the first most similar item is the item itself, because it is within the 100,000. This is where we sampled from, right? And here we can see that its similarity is very close to 1. So of course we have some losses due to due to number operations approximations. We were doing some summation of 500 numbers many times, and so it's not 100% 1, but to the 1, 2, 3, 4, 5, only at the 5 decimal point there's some inaccuracy. So that's considered usually quite good. And okay, so the most similar are another red pants that look almost the same, so that's very good. It's very close to 1 similarity. Then further away there are similar color pants, but they are not exactly the same. And further away again, we can see these pants which have different color but similar shape. Okay, so yeah, this search very well. So building of the index took us time, but actual search over 100,000 was super fast. Okay, and we are using just images, right? So so we search across different language. We could do the same thing now we did with the images. We could do that with text, and we could do that with summation of both, and it works. Okay, so that's it, right? So we used our GLAMI 1M image text classification dataset to do zero-shot classification. We did search across items using just images, and we used models which were trained on the images and captions from the internet, and they had nothing to do with our data set, and it already worked. We were already able to do a little bit of classification. So do you have any questions? Do you feel like there's something missing, or you are something misunderstanding? We'd like to accelerate learning and research. And so have questions. Do you have any ideas for research that could be replicated in public? You can use our dataset for this. If you have any questions regarding this, reach out to us via email or social platform mentioned. You can read more about dataset on these links. And as well, attend the future meetups. Okay, thank you very much. This was Václav Košař on hands-on machine learning with multilingual image text fashion dataset. Join us in the future meetup, and goodbye.